All right. Welcome back, everybody, to the deep dive. We've got a really interesting topic today.
Yeah, I'm really excited for this one.
So today we're diving deep into how antimicrobial agents interfere with nucleic acid synthesis. So essentially how we fight infections by going after the DNA and RNA of those microbes.
Right.
And, this is the very essence of life for these little guys, so it's pretty crucial, right? We've got some scientific papers here that break down how some drugs disrupt those fundamental processes: replication, transcription, nucleotide synthesis.
It's incredible. It's like a molecular battle.
Exactly.
Yeah.
And we want to understand how these drugs target those mechanisms, giving you guys a better idea of how they actually work.
I think that's what's so fascinating, getting down to that level of detail. It's like you said, understanding how these medicines work.
Exactly. So why don't we jump right in? Let's start with how we mess with DNA synthesis. Fluoroquinolones, what are they all about?
Oh man, fluoroquinolones, they're so precise in how they work. It's kind of amazing.
How so?
Well, they target these bacterial enzymes, DNA gyrase, or it's also called topoisomerase 2,
Right.
and also topoisomerase the fourth. Now think about these enzymes like, imagine a really tangled ball of yarn.
Okay, I can see that.
These enzymes are essential for managing all that, for keeping that DNA structure in check.
So it's basically untangling that yarn, preventing it from becoming a huge mess.
Precisely. And that's where fluoroquinolones come in and sort of sabotage the whole thing.
Sabotage how?
So when gyrase goes to cut that DNA, just to relieve tension, the fluoroquinolone steps in and basically says, nope.
Okay.
It stabilizes that broken state, doesn't let the DNA get resealed.
Oh, wow.
And what happens? You get double-strand breaks, really bad news for the bacteria, especially when they're trying to replicate.
Yeah, can't really recover from that, can they?
They're done for, bactericidal, as we call it. It kills them dead.
So that's how we disrupt DNA synthesis. But what about RNA synthesis? That's a different process altogether, right?
Absolutely. Different process, different target. This is where rifampicin comes into play, one of the rifamycins.
Okay, so rifampicin, how does that work?
So this one goes after bacterial RNA polymerase, the enzyme responsible for making RNA from DNA.
Okay, yeah.
Now, the key here is it blocks the very beginning of RNA production, preventing the formation of those first bonds. It's like stopping the first domino from falling.
I like that analogy, stops the whole cascade.
Exactly. And just like fluoroquinolones, messing with such a fundamental process makes rifampicin also bactericidal. No RNA, no life for the bacteria.
Makes sense. So we've seen how to disrupt DNA synthesis and RNA synthesis. But what about the raw materials, the building blocks themselves?
Ah, you're talking about the nucleotide precursors. This is where things get even more interesting. We go after the bacteria's ability to even make those building blocks.
Right, and I remember this being a really clever approach.
Oh, absolutely. This is where we leverage the differences between bacterial cells and our own cells.
Exactly, target what makes them unique.
Right. And a key difference lies in how we get folic acid.
Okay, folic acid, remind me.
So bacteria, they have to synthesize their own folate, which is crucial for making those nucleotides. We, on the other hand, we get it from our diet.
Oh, right. So that's our opportunity.
Exactly. That's where sulfonamides and trimethoprim come in. They exploit that difference.
Okay, I've heard of those. I actually think I took trimethoprim once for a UTI. So can you break down how they work?
Sure. So sulfonamides, they're structurally similar to pebera, or paraminobenzoic acid.
Okay.
And they target this early enzyme in the folate synthesis pathway called dihydroapterate synthase. They basically block it.
So they prevent the bacteria from even getting started on making folate.
Precisely. Now, trimethoprim comes in and inhibits a later enzyme in the pathway called dihydrofolate reductase.
So it's a 1-2 punch.
Yeah. And you know what? That combination, it's more than just the sum of its parts. Blocking 2 steps in a row, that's where the magic happens.
So it becomes more powerful.
You get this synergistic effect. Often it makes the combination bactericidal, actually killing the bacteria. Whereas individually, they're usually just bacteriostatic. They just stop the bacteria from growing, but don't kill them outright.
Interesting. So disrupting the folate pathway, another way to tackle bacterial infections. We've covered a lot, but there's one more I wanted to touch on. What about just damaging the DNA directly?
Ah, yes. You're talking about the approach taken by nitromidazoles like metronidazole.
Yeah, and I know this is particularly relevant for those anaerobic bacteria.
Absolutely. You see, metronidazole is what we call a prodrug. It's inactive until it gets into an environment with low oxygen.
So it needs to be activated.
Exactly. And that's perfect for targeting anaerobic bacteria since they thrive in low oxygen environments. Once activated, though, metronidazole becomes this wrecking ball.
Okay, how so?
It causes breaks in those DNA strands, and that just halts DNA synthesis altogether. And that's pretty much game over for the bacteria.
Another clever approach. So I think it's fascinating how we're able to exploit these fundamental differences between microbes and our own cells.
It really is. It's like finding those Achilles heels and targeting them strategically.
Yeah, and it seems like we've got a pretty diverse toolkit for doing just that. We can mess with their DNA replication, their RNA production, even the building blocks they need.
And it all boils down to targeting those crucial pathways, the ones that are essential for their survival, but distinct enough from our own processes that we can hit them without harming ourselves.
That's the key. So to kind of bring this deep dive to a close, it's amazing how these antimicrobial agents can be so targeted and so ingenious in how they work, right?
It really is remarkable. But, thinking about all this, about how these drugs target those processes, makes you wonder, how do we keep up?
Keep up with what?
Well, with resistance. You see, the more we learn about these precise mechanisms, the more we understand the immense challenge of developing new antimicrobials, especially when bacteria are constantly evolving and becoming resistant to our existing drugs.
That is a big question. How do we stay ahead of the game?
Well,
Something for all of us to ponder. Thanks for taking this deep dive with us. And until next time, keep those brains buzzing.
absolutely. It's been a pleasure.